Okay, so now let's do one example. Air undergoes a polytropic process in a piston cylinder assembly, and the PV square is equal to constant. That means the index N is equal to constant. P1 initial pressure is 1 atm, T1 initial temperature is 20 Celsius, P2 final pressure is 5 atm. CV specific heat at constant volume of air is also constant. The value is 0.72 kilojoule per kilogram per Kelvin. We look for two things. The first one is work per unit mass. The second one is heat transfer per unit mass. Let's start from the first one, looking for work per unit mass. So we're going to use the equation we just derived earlier, which is work equal to mR times T2 minus T1 divided by 1 minus n. To use this equation, you have to satisfy two requirements. The first one is polytropic. Yes, this process is polytropic. The second requirement is it has to be ideal gas. And for air, we can always assume it's ideal gas. Alright, so let's take a look. Because we're looking for work per unit mass, so we move mass to the left-hand side. It becomes W over mass equal to R times T2 minus T1 divided by 1 minus N. Let's take a look. Do we have R, gas constant? No, we do not. Do we have final temperature T2? No, we do not. Do we have initial temperature T1? Yes, 20 Celsius. And do we have the index N? Yes, N is equal to 2. So to solve for work per unit mass, we just need to look for two things. The first one is R, gas constant. The second one is T2, final temperature. How do we look for R? Let's recall. R is equal to R bar divided by molecular weight. We have this equation to use. And R bar is constant. R bar is 8.314 kilojoule per kilomole per Kelvin. That's the unit for R bar. R bar is called a universal gas constant. The value of R bar never changes. MW stands for molecular weight. What is the molecular weight of air? Molecular weight of air is 29. 29. And what is the unit for 29? You have two options. You can either use gram per mole or kilogram per kilomole. They are equivalent. So here I use kilogram per kilomole. And why? Because the two kilomoles will cancel each other. So the solution for R is 0.287. And what is the unit left? It's kilojoule divided by kilogram divided by Kelvin. That's everything left. So now we found R, gas constant for air. So the only thing I need right now is T2, final temperature. Which equation we have that involves T? Probably ideal gas equation. So now we start from ideal gas equation. PV equal to mRT. So now we're going to apply this equation twice. The first time we apply to the initial state, so P1 times V1 equal to mRT1. There's no need to add a subscript to mass or gas constant because they do not change. And then we apply the same equation again, but this time to the final state. So it becomes P2 V2 mRT2. And then what we do is to use left-hand side divided by left-hand side. It must be equal to right-hand side divided by right-hand side algebra. So now we can easily tell we can get rid of mr. They cancel each other because we're looking for T2. So what we do is to move T2 to the left-hand side. And from algebra, we know T2 is equal to T1 times P2 over P1 times V2 over V1. Okay, do we have P2? Do we have T1? T1 is the initial temperature. Yes, given, 20 Celsius. Do we have P1 and P2? Yes, they're both given. The only thing we don't know is V2 over V1. V2 over V1. How do we look for V2 over V1? Let's recall. It's a polytropic process, and PV squared is equal to constant. So now we can apply this equation again twice. The first time to the initial state, second time to the final state. Because the value is constant, so initial P1 V1 squared must be equal to final P2 V2 squared. And from here, we can find V2 over V1. And V2 over V1 is equal to square root of P1 over P2. And now we can plug in this new expression of V2 over V1 back into the previous equation. So now the new equation for T2 becomes T1 times P2 over P1 multiplied by square root of P1 over P2. And this becomes T1 times square root of P2 over P1. So now we can just plug in the numbers. T1 is given as 20 Celsius. We cannot directly use 20 Celsius because it's not SI. So convert it to SI by adding 273. Multiply by, okay, P2 over P1, they are both given in ATM instead of Pascal. It's okay to just directly use ATM because this is division. The two ATMs will cancel anyway, so there's no need for us to convert them. But if you want to make sure, you can always convert everything to SI. One ATM is equal to 101325 Pascal. Okay, so the solution for T2 here is 653, and the unit must be Kelvin. So now we can go back to our equation and take a look. This is our right-hand side. Do we have R and a T2 now? Yes, we have both. So to look for work per unit mass, that's pretty easy, just plugging all the numbers. Okay, so W over mass, like before, is R times T2 minus T1 divided by 1 minus N. So now we plug in numbers. R is 0.287, and be careful here. Why? Because the unit is kilojoule per kilogram per Kelvin, and a kilojoule is not SI, so we need to convert kilojoule to joule, which is SI, by multiplying 1000. SI unit times T2, 653 Kelvin, SI unit already, minus T1. T1 is given as 20 Celsius, so convert it to Kelvin first. And then divided by 1 minus n. The index n is given, which is 2. So now our solution is negative 103.2 times 10 to the third. And because I used SI unit for everything in the right-hand side, the solution must also have SI unit. The SI unit for work is joule divided by mass. The unit for mass is kilogram. So this is the unit. And then we do one more step, negative 103.2, convert joule to kilojoule. Okay, so this is the solution for work per unit mass. And this number is negative. What does that tell you? If work is negative, that means the system consumes work. Consumes work. If work is positive, that means system generates work. Okay, so that's part one, work per unit mass. And then we'll do part two. Part two is to look for heat transfer per unit mass. We have already found work, and now we're looking for heat transfer. Which equation goes to your mind? Probably first law. Q minus W equal to delta E. And before you apply this equation, you should always double check if your system is a closed system, because that's the requirement you have to satisfy before using this equation. Okay, so what we have is a piston cylinder assembly. There's no inlet, no outlet, so of course, it's a closed system. So yes, we can use this equation. And just like before, delta E has three components, delta KE, delta PE, and delta U. And then just like before, we can neglect delta KE, delta PE. We can neglect delta KE because the initial and final velocities are both zero. We can neglect delta PE because there's no change in height. Okay, so now what we can have is Q minus Q is equal to W plus delta U. And then again, because we're looking for heat transfer per unit mass, so we divide every term by mass. It becomes Q over M equal to W over M plus delta. What is capital U over M? Capital U over M is lowercase u, specific internal energy. So now let's continue. W over M plus, what is delta lowercase u? Delta means change. To calculate change, we always use final minus initial. So it becomes lowercase u2 minus lowercase u1. Okay, and so now let's take a look. Do we have W over M? We already found work per unit mass from part 1, and the question goes down looking for specific internal energy U2 and U1. Okay, how do we look for lowercase u? You have two options. The first one is to go to the table, and the second option is if the substance is ideal gas, you can use an equation to calculate u. What is that equation? The equation is u is equal to Cv times T. Okay, so because we're dealing with air, which is ideal gas, so we can use this equation to calculate U. Okay, so let's continue. W over M plus U2 will be rewritten to Cv times T2. U1 will be rewritten to Cv times T1. There's no need to give Cv a subscript because Cv, like the problem said, is a constant, so it doesn't change. All right, so now let's take a look. Do we have the first term in the right-hand side? Yes, we found it. Do we have Cv? Yes, it's given. Do we have T2 and T1? Yes, we have everything. All right, so now what we can do is we can do one more step. W over M plus take Cv out of those two terms. So it becomes T2 minus T1. All right, let's plug in the numbers. W over M we found from before is negative 103.3, and the unit is kilojoule per kilogram, plus Cv. What is Cv? Cv is given, it's 0.72, and also kilojoule per kilogram per Kelvin, multiplied by T2. T2 is 653 Kelvin, minus T1. T1 is 20 Celsius, which is 293 Kelvin. So now, if you use, let's do the units. Kelvin cancels Kelvin. Then kilojoules plus kilojoules per kilogram plus kilojoules per kilogram. So the solution must have a unit of kilojoule per kilogram. Okay, and then you can use your calculator. Your solution is 159.2. Okay. So now this is the solution in kilojoule per kilogram. If you're not still comfortable with the units, you can always convert everything to SI unit, which is joule per kilogram or joule per kilogram per Kelvin. And then from there, your solution will be in SI unit, which is joule per kilogram. And then you take one more step to convert joule to kilojoule. Okay? Okay, so now our solution for heat transfer per unit mass is 159.2 kilojoule per kilogram. And the solution is positive. What does that tell you? If heat transfer is positive, that means the system gains heat. If heat transfer is negative, that means the system loses heat. Okay?